I hope this is recording. Hey, hey, looks like it. All right, so this, ladies and gentlemen, is that problem that we worked on in class last week, just a few days ago actually. And it was this curve is a Stokes problem, but we're not doing Stokes. We're doing the line integral in 3D. So it's kind of like Stokes because it's a line integral in 3D technically. So it's a line integral the usual way. That's why the little circle here, because it's a simple closed curve, but it's in a three-dimensional arrangement. You know, these three segments are written out. Now, if you already have all this in your notes, I just want to point out the spot that has the correction. It's a very small correction. So the goal, remember, we did this problem the short way using Stokes' theorem, where we turned it into a surface integral, and then redid one of the options with the surface integral and got -3. So now we're going to try and get -3 again, and here's how close we were. We were so close. C1, we did right. C2, we did right. C3, that's where the problem was. We made a mistake on the third one. So that kind of makes sense to me because we were going, we were hot. You know, the problem is great. It's starting out at the beginning, we're sharp. But by the time we got to that third integral, we're all just burnt. You know, so we missed something. Well, here's what we missed. I didn't write down all the details. Here's the vector field. Here's R3. I didn't write down R1, R2 because we don't need it. So here's R3. Remember what we got to do is we got to do substitute in t for every occurrence of x, 5 minus 5 over 2t for every occurrence of z. So there's going to be a z squared here. But y being 0 kills off those two. So these two zeros were right. But we have this long z coordinate thing. And then we have to dot it with the derivative of the r. So this is the dr dt. And 0 to 2, just from the parameterization, just trying to get that segment that starts at 0, 0, 5 and comes down to 2, 0, 0. All right, so everything's in place. Do the dot product, and there's the dot product, and there's the mistake. We didn't have that 8. I think we had a 4. We were off by a factor of 2 right here. That was the mistake. So if you go in your notes, find this spot. You don't have to change anything else but that spot, and then finish this calculation. So I've written here, it's very hard to read, integral C1 plus integral C2 plus integral C3. It looks just like squiggles plus squiggle plus squiggle. But it's the first two curves don't change anything, they're fine, but add C3 to it, and the C3 came out to be -125 over 120 over 3. And if you go back to the originals, the first one was -3, the next curve gave us a 125 over 3, and this one was -125 over 3, giving us just the -3, which is the answer we wanted. We should have caught this because we had the first piece going to -3, but we hadn't done it with the Stokes theorem yet. So we didn't know that -3 was the answer. If we had known -3 was the answer, we might have caught that these two have to cancel then, and we would have known where to look. That's how I found the mistake, was these two have to cancel out. So I went snooping, and I thought, you know, I have a 125 over 3, and then I've got these numbers that are all in the neighborhood. Look at all these 125s on the C3, and C2 was already 125 over 3. And any of you would have thought of this. If we can just get a -125 over 3 out of this thing, we match the shortcut answer. So that's it. I was thinking of preparing a bunch more problems for you, but you know, you guys are smart. You've been doing your math all along. On Wednesday's class, you're going to bring me a test. We're going to have 2.5 hours or 2 hours and 15 minutes. And we'll just do problems. Do problems, do problems, do problems. It's going to be good. And then final exam, I'm not worried about it. You guys just put it all together. Put it all together during Wednesday's class. That's good timing. I'll see you then. And now I'm walking over and shutting it down.